Hi there, this is Professor Barber. This lesson is titled More Trigonometric Graphs. In this lesson, we extend our graphing skills to the cosecant, secant, tangent, and cotangent. Upon successful completion of this lesson, you will be able to graph the tangent, cotangent, secant, and cosecant functions, and 2, be able to graph transformations of the tangent, cotangent, secant, and cosecant functions. Roman numeral 1, graphs of cosecant, secant, tangent, and cotangent functions. Part A, cosecant and secant functions. The cosecant and secant are also periodic, and their period is 2 pi. That means the cosecant of x plus 2 pi equals the cosecant of x, and the secant of x plus 2 pi equals the secant of x. The cosecant and secant functions are reciprocals of the sine and cosine functions, respectively. So we know that the cosecant of x is equal to 1 over the sine of x, and the secant of x is equal to 1 over the cosine of x. The graph of y equals cosecant of x has vertical asymptotes at x equals m pi for n an integer. Notice that is where the sine function equals 0, and you cannot have zeros in the denominator. Let's look at it for the secant. The graph of y equals secant x has vertical asymptotes at x equals pi over 2 plus n pi for n an integer. Again, those are the values this time where the cosine equals 0. Graph the function y equals cosecant of x. Let's approach this by looking at y equals cosecant of x, the reciprocal function 1 over sine x. Okay, so first thing I'm going to do is make that recognition. The next thing is I'm going to sketch the sine function. So let's go ahead and mark on the y-axis a point that will denote as the height of 1 and below 0 as negative 1. I'll pick 4 key points for the sine function, which include 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi, and we will connect the sinusoidal curve. Now, we've got the sine, and we know that sine of x is in the denominator part, so let's now sketch the vertical asymptotes. And the nice thing here is we draw the vertical asymptotes every place the sine crosses the x-axis. So the y-axis will also have one vertical asymptote at pi, another one at 2 pi, and because this is periodic, we know that we will have a vertical asymptote at every integer interval times pi. The cosecant function is its reciprocal, and so to draw it, and you can sketch a few points later, but so that you get the general idea, it touches at the highest point, which would be pi over 2, 1, turns back around and increases asymptotically. And it repeats, so now in the next interval, which would be from pi to 2 pi, along the asymptote, it increases all the way up to 3 pi over 2, negative 1, and then goes back down. The important thing to remember here is that the graph is not the sine curve. The graph bowl-looking curves that either are open up or open down. Graph the function y equals secant x. I'm going to begin by acknowledging that y equals secant x. That's a reciprocal function equivalent to y over cosine x. The next thing I will do is sketch the cosine function. So to do that, on the y-axis, let's mark some number intervals. One dashed line above 0 will be 1, and then one dashed line below 0 will be negative 1. I will pick 4 select points so that I have a guide for my cosine. 0, negative 1. and then pi over 2, 0, pi, negative 1, 3 pi over 2, and 2 pi, 1. Let's connect the points knowing the general shape of the cosine curve. Okay? So now we have a cosine curve. The next thing I'm going to do is sketch the vertical asymptotes for the secant function. The vertical asymptotes occur every place you get a 0 in the denominator, and so we're going to draw vertical asymptotes through every place where the cosine touches the x-axis, because that's where it's 0. The first one I'll draw will be to the right of 0, and it's a vertical line through pi over 2. Go over a pi unit, and then we'll go and draw a vertical line through 3 pi over 2 and get the idea that this is a periodic function, and so it repeats every that many units. Now we can sketch the y equals secant x, knowing that it is a reciprocal function with, we've got these vertical asymptotes as guidelines. So we'll start at, let's go to 0, 1. The secant will increase upwards to the vertical asymptote. It'll be symmetric to the left of the y-axis, so it'll increase that way also. Let's go to the interval between pi over 2 and 3 pi over 2. The graph will increase from negative infinity close to pi over 2 all the way to pi negative 1, then turn around and decrease, and it'll go back down along the asymptote 3 pi over 2. And let's do one more at 2 pi. Will increase. It's upwards on both ends. Now what's important again for me to stress is that the graph is not the cosine part. The graph is not the vertical asymptote. The graph of the secant function are the split parts that look like parabolas. They're not parabolas, but that's what it looks like. Roman numeral 1. Graphs of cosecant, secant, tangent, and cotangent functions. Part B. Tangent and cotangent functions. The tangent and cotangent functions are also periodic, but their period is pi. So the tangent of x plus pi equals the tangent of x, and the cotangent of x plus pi equals the cotangent of x. The tangent and cotangent are ratios of the sine and cosine functions. We know tangent x is equal to sine x over cosine x, and cotangent x is equal to cosine x over sine x, respectively. The graph of y equals tan x has vertical asymptotes at x equals pi over 2 plus n pi for n an integer. Let's observe. The graph of y equals tan x has vertical asymptotes where the cosine function equals 0. Let's continue. The graph of y equals cotan x has vertical asymptotes at x equals m pi for n an integer. And let's note that the graph of cotan x has vertical asymptotes where the sine equals 0. Graph the function y equals cotan x. Let's approach this by first rewriting cotan x as its ratio identity, which would be cosine x over sine x. Now, from this we can find our vertical asymptotes. We're going to have vertical asymptotes where sine of x equals 0. And that happens at x equals 0, pi, 2 pi, dot, dot, dot. So I'll draw vertical asymptotes through the y-axis. Draw, please, through pi and 2 pi. Now, the next thing I'm going to do is look for x-intercepts. X-intercepts occur where the numerator equals 0, and so this is where we've got cosine x equals 0. And cosine x equals 0 at x equals pi over 2, at 3 pi over 2, at 5 pi over 2. You get the picture. So I'll go ahead and do that. I marked pi over 2 and 3 pi over 2. The one last thing that I would like to do is find some points between 0 and pi over 2. So I'd like to evaluate the cotangent of pi over 4. And we know that to be 1. So we'll mark pi over 4, 1. And let's go ahead and evaluate the cotangent of 3 pi over 4, and that's midway between pi over 2 and pi, and that's equal to -1, so we'll mark that. Okay. If you plot a sufficient number of points, you get a cotangent curve that looks like a stretched out cubic, and it is periodic, so it repeats in the interval of pi indefinitely. Make sure that you can do this for the tangent x curve as well. Roman numeral 2, graphs of transformations of tangent and cotangent functions. The functions y equals a tan kx and y equals a cotan kx for k strictly greater than 0 have period pi over k. To graph one period of y equals a tan kx, an appropriate interval is opened parentheses negative pi over 2k, comma pi over 2k, open parentheses. And to graph one period of y equals a cotan kx, an appropriate interval is 0, comma pi over k, both ends open. Graph the function y equals the tangent of x minus pi over 4. What we have presented here is a phase shift, and so the x minus pi over 4 tells us we have a phase. Remember, phase shift means a horizontal shift of positive pi over 4. So we take whatever is the standard graph of the tangent function and plop it over to the right, pi over 4 units. Let's begin with a standard tangent graph. So if y equals tan x, the standard or your basic tangent graph, knowing that the tangent is sine over cosine, we have vertical asymptotes every place where the cosine is 0. So we'll do this at minus pi over 2, and at positive pi over 2 we'll also draw vertical asymptotes. You plot a sufficient number of points, and we learn that at minus pi over 4 the tangent is -1, and at positive pi over 4 the tangent is +1, and we connect some points and we get a curve that starts in the bottom, increases, crosses the origin, continues to increase within the bounds of the asymptotes. Now, to incorporate the phase shift of pi over 4, I'll take the vertical asymptote at minus pi over 2, shift it to the right pi over 4 units. So the new vertical asymptote, or the shifted vertical asymptote, would be at negative pi over 4. Then take the pi over 2 and again shift it a positive pi over 4 units. So this would be at 3 pi over 4. Now let's find the midpoint. And the midpoint, that's the middle of negative pi over 4, and this should look more like a pi. 3 pi over 4 would be just plain old pi over 4. So that's where we would have the intercept. Let's draw the graph. And now we have successfully taken the graph of tan x and phased shifted pi over 4 to the right. Roman numeral 3, graphs of transformations of secant and cosecant functions. The functions y equals a cosecant kx and y equals a secant kx for k strictly positive have period 2 pi over k. An appropriate interval on which to graph one complete period is brackets 0, 2 pi over k. Graph the function y equals secant 2 times the quantity x minus pi over 4. In order to graph this function, what we do, or what you need to do, is just graph y equals the cosine of 2 times x minus pi over 4. And so let's find some key parts. We need to find the period. The way to find the period of sine, cosine, secant, and cosecant is 2 pi over k. And in this problem, the k within the argument is the number 2. So we get that the period is now pi. Now, the phase shift, we've got x minus pi over 4. So the phase shift is pi over 4 to the right. An appropriate interval, one that'll give us all of the characteristics for one complete period. We can do this by starting at pi over 4 and then adding the period to it. So we would do pi over 4 plus the period of pi. And so that gives us pi over 4 to pi over 4 plus pi would be 5 pi divided by 4. Let's graph the cosine. I'll mark some key points. I'm going to mark the phase shift pi over 4, so it's on my xy axis. I will go ahead and also mark the equidistant point between pi over 2 and pi, which would be 3 pi over 4, and the point where we finish the graph, which would be 5 pi over 4, or where we get the one complete period. Okay. Now let's sketch the cosine. There's no change in the amplitude, so we'll mark the high point, the 0, -1, the 0, and the 1. And so we now have sketch of the cosine function. So if you were asked for the cosine, you would be done. However, the secant is the reciprocal, remember? And so in order to go to the secant, okay, we need to remember that secant t, I'm going to use a different variable not to confuse it with the one we're working with, is 1 over cosine t. So let's draw vertical asymptotes every place we have a cosine intersecting the x-axis. That's where we have a 0. And then we can write the reciprocal portions, or sketch the reciprocal portions using the asymptotes and the cosine function graph as guides. So we'll draw secant, then secant, secant, and secant. Again, let me remind you, the cosine portion nor the vertical asymptotes are part of the secant graph. Those are the guidelines we need in order to be able to graph the reciprocal functions.